Hello, so my name is Kwon from Maryland Cybersecurity Center. Today I'll present Beewolf, which is a system for detecting silent delivery campaigns. Our paper is titled Catching Worms, Trojan Horses, and PUPs, Unsupervised Detection of Silent Delivery Campaigns. This work is done with Virinchi, Srinivas, Amol, Deshpande, and Tudor, Dumitras from University of Maryland, College Park. So how does malware get delivered these days? So there are very few malwares that self-propagate, and most of the malware these days use these services called malware delivery networks and get distributed as a campaign. So these services have a business model of charging fees for delivering malware or PUPs. And how it works is that they have these malicious downloaders injected in the host that access to this remote server and deliver payloads. And in order to keep their business going and deliver these payloads, they have to remain silent. So that's why they orchestrate the silent delivery campaigns. So how does this silent delivery campaign look like? This is a real-world example of a silent delivery campaign where they utilize 3 malicious downloaders across different hosts. And these downloaders access to this domain within a short time window and deliver payloads. After a few days of inactivity, they change to another fresh domain and deliver payloads. And another several days later, they now move to this domain and deliver payloads. However, in this case, there's a payload that turns out to be another downloader that access to this domain and deliver payloads with the existing downloaders. So this reflects a coordinated action among these downloaders across hosts. So there has been prior works on studying different of these entities. First, there has been machine learning studies identifying malicious domains, looking at detection of malicious downloaders. And there has been measurement studies on the payloads. However, in this work, we want to focus on this act of coordination. That is a strong signal for detecting silent delivery campaigns. So that is defined as a lockstep behavior. So the lockstep behavior can be represented in this form of a bipartite graph, where the left-hand side nodes are downloaders, which are more stable than the right-hand side nodes, which are the domains. And they act in a coordinated fashion in terms of changing and accessing domains. So there has been prior works on focusing on this lockstep behavior to detect malicious entities, especially in social networks. However, they either require these seed nodes, which is not suitable for in our case, where we have see a large detection lag in the downloaders, and it requires interpreting events defined by multiple features. And also, it's not designed for streaming data, which is not feasible in the case because we see some high churn in the domains. So we introduced Beewolf, where we propose an unsupervised and deterministic technique, which is orthogonal to the work of detecting these malicious downloaders and domains that using machine learning, and that can operate on the stream of download events. Also, which we can find some interesting relationships, which is hidden by using this prior works. So what are those relationships? By using this lockstep behavior detection, we can also not only detect these direct download relationships between downloaders, but also we can find out some hidden indirect relationships that can expose the hidden dependencies in the underground economy. That can lead us to suggest suitable interventions for disrupting the malware delivery. So that was the introduction of my presentation, and this is the outline of today's talk. I'll first go on to system overview. So this is a system diagram of Beewolf, which consists of 2 modes, offline and streaming. Offline is mostly used for data analysis. We take the download events data as an input. We also have a whitelisting phase where we filter out the download events from benign downloaders. As the input data set, we use the data set from the dropper effect paper from CCS 2015. It has download events consisting of downloader, domain, and the payload, and the corresponding server timestamp from the year 2013. We collect some ground truths for labeling. We use VARSolo for maliciousness, NSRL for benign and whitelisting, And we also refer to some underground forums and knowledge base to understand the publishers. So Beewolf can detect these lockstem patterns in the offline mode from the entire input data set. And for streaming, we detect these from the stream of data. Beewolf has 4 core components, including star detection, galaxy graph, FP tree construction, and lockstep detection. So how does this work? So the goal of these 4 components is to detect a lockstep. A lockstep here is the example of a lockstep where it consists of downloader ABC and domains large ABC, and it is it detects locksteps we define as a nearby click, which is a complete by click with some missing edges with a time constraint. I mean, we build edges within time delta t. So the first component in Beewolf is the star detection, where we detect stars. A star is a complete bipartite graph of a single domain and at least 2 downloaders. Then we have a galaxy graph, which is the bipartite graph of consisting of set of stars. So we built the galaxy graph incrementally by using the stars. Then we go into FP tree construction using the galaxy graph. Especially, we use the adjacency list of this galaxy graph. So this FP tree algorithm is an algorithm that's widely used in the graph mining community to detect complete byteclicks. So it starts from the root, and it creates the FP tree where the nodes are the downloaders with left-hand side nodes, and each of the nodes have an attribute, which is the domain, which is the right-hand side nodes. And this is the full picture of the FP tree you will get from the galaxy graph here. So after we get this FP tree, we detect locksteps. So how do we do it? So interesting thing is that the FP tree is passed from the root to a certain node in the FP tree, reveals a complete byteclick. So for example, here to root to B, the path CB and its attribute large BCA forms a complete byteclick shown in the left. However, remind that we are trying to detect nearby clicks as locksteps. However, the original algorithm doesn't allow us to do this, so we introduce some heuristics for detecting nearby clicks using this FP tree. And also, there are another limitation on the former original algorithm. So for in this case, we see this complete byteclick of CE and large CD. However, it doesn't show up in the FP tree. Instead, it just shows some graph of these complete byteclick. So we introduced a supplementation phase, which is an independent process that can be done in parallel, and that helps us to recover these missing parts. And for the details, they are presented in the paper. So that was the system overview. Let me go into the analysis. So for lockstep analysis, we run Beewolf in offline mode, which take a time window delta of 3 days, which is shorter than the typical reaction time of the domain blacklisting. In summary, we have lockstep total 67,000. In order to understand what these locksteps are, we try to label them. We first label them by the publishers who signed the downloaders in order to identify the organizations. Here we introduce this term of representative publisher, RepPub, which is the publisher that accounts more than half of the signed downloaders in the lockstep. So to give you an example, let's say that there's 3 downloaders down by Outbrowse, MyNAD Ltd in the lockstep. In this case, we say the RepPub is Outbrowse. And in the case we cannot identify the RepPub, we place it in the mixed category. So in total, we have 6 categories, including PUP, PPI, benign, and other. And these namings and the labels will be further used in the graph representation. And in result, we have 300 RepPubs. We investigated the top 50 RepPubs according to the order by the number of locksteps they have. It's in our paper. We see that large portion of the locksteps correspond to the mixed category, followed up by the PUP. So this shows that it's actually difficult to place a lockstep using the publishers in the specific categories. So we take another attribution method. We try to label them by the payload they distribute. So in order to understand the purpose of the lockstep and use it further for the detection performance evaluation. So we take 2 steps. First, we label the downloader by the payload they distribute. We say that downloader is a malware downloader if it distributes malware. we say that it's a PUP downloader, PUD, if it's distributed no malware but at least one PUP. And we have benign downloaders and unknown downloaders following the same convention. Then we label the lock steps based on the downloader labeling. So we have first malware downloader lock step, MDL, which is a lock step that includes at least one MD. And we have PUP downloader lock step, PDL, which contains PD but no MD. And we have unknown downloader lock step and benign downloader lock step. So we say this MDLs and PDLs are suspicious lock steps. And we say benign downloader lock steps are benign. And the unknown downloader lock steps, we treat them as we fail to label. So in result, we have a higher success rate in terms of labeling. We only have 2.3 unknown downloader lock steps. And we find that these malware downloader lock steps occupy more than 80% of the total lock step, while the benign downloader lock steps are low. And this reflects our community's effort on labeling and detecting malware rather than looking at the client-side distribution infrastructure. So that was the summary of the lock steps. Let me go over to show you some interesting observations we made. We find some overlap between malware and PUP delivery ecosystems. We focus on the overlap of downloaders, where we find about 37% of the downloaders are presenting in both malware downloader lock steps and PUP downloader lock steps, which is associated with most of the PDLs. We also compare with the publicly available mal-signed blacklist, where we find almost 2,000 downloaders signed by 200 publishers appearing also in our lock steps, which is involved in almost 70% of malware download lock steps and 37% of the PDLs. So this suggests that many PUP publishers are likely involved in malware delivery. However, recent measurements of commercial PPIs did not find substantial overlap between these ecosystems. Therefore, we find some key distinctions between their study and ours. One of the studies have some geographical distribution difference. They mainly focus on USA, where we have hosts from 72 different countries, and there are some differences in the observation period and malware. However, most important is that Lockstep detect these indirect relationships, which means there's no direct download relationship between the downloaders, but nevertheless they appear in the Lockstep. So we find some cases like there are unsigned downloaders appearing in Locksteps that deliver malicious payloads. And so that was about the overlap. Let me go into some unique business relationship we find. So we focus on the publishers appearing together in locksteps, which is evidence that they utilize the same server-side infrastructure. We here introduce two different publisher relationships, including partner, which are the downloaders that are in direct downloaded by relationships, and there's neighbor, where the downloaders are having no direct download relationship but appearing together in the lockstep. This either implies that they are organizations that use multiple co-signing certificates, or they have relationship through a common third party. So this is an example representation of the business relations graph we present in our paper, where the nodes are the publishers and the edge are the business relationship, either the partner or the neighbor. And we run some community detection algorithm to identify the communities. So here's the example community Outbrowse Ltd in the left corner. The nodes here are either the advertisers or the affiliates of the PPI, like the Multiply ROI or the MineAD Media Ltd, or the variants of the RepUp certificate, like the Outbrowse Ltd or the Outbrowse. So this exposes the organization utilizing certificate polymorphism, like the Outbrowse Ltd, Browse, and organizations sharing the same service-side infrastructure. So that was so let me go into the evaluation. So we also evaluate streaming setup. We look at the batch of download events from year 2013. We set the time window of delta T per batch in 3 days. And we have 122 batch in total. We check the computation cost growth. So we first run the in serial manner. So these are the 4 components, and their computation costs increased by the batch, and the cost is here in log scale. By summing up these 4 components, we get the total runtime. As you can notice, the lockstep detection time is most dominant. We see a slowdown of 7.7 seconds per batch until we reach 100 batch, which is approximately 300 days, and which grows up to 20 minutes in total. After the 100 batch, we see overhead increase and the due to the supplementation time. However, note that the supplementation time are independent, so we can introduce some parallelism. So we run some simulation, assuming that we have optimal parallelism where we have enough nodes to process. So here's the result. We see linear growth in the lockstep detection time with slowdown of 0.1 second per batch. So I will conclude. We introduce Beewolf, which is an unsupervised and deterministic system which operates on the stream of data. We discover an indirect relationship which reflects the overlap between PUP and malware ecosystems. Note that Beewolf can be used beyond malware detections. You can be used in other kinds of coordinated actions like beaconing, CNC communication. So we also really talk about the data release in the following website. So please check. Thank you, and I'll be glad to answer some questions.
Hi. Could you go back to the comparison with the use